Section 3.1 is titled Numeration Systems. And what we're going to do in this section is that we're going to sort of take a look back. We're going to take a look back at how different civilizations have done mathematics in history. Okay, we're going to take their numbers and our numbers, we're going to compare them. We're going to look at some addition and subtraction things and conversions. We're also going to talk about why we don't use some of their systems anymore and some of the problems that there are inherent in their systems. So the first one that we're going to take a look at is, or talk about, is our system. Our system, whether you knew it or not, is actually called the Hindu-Arabic numeration system. It's a numeration system we use today. It was developed by the Hindus, excuse me, and transported to Europe by the Arabic. So a few facts that you know but probably had not thought about in these words before. All of our numerals are constructed from 10 digits. What is our smallest digit? 0. What is our largest digit? 9. So 10 is not a digit. It's a 2-digit number. Okay? So the single digits, there are 10 of them from 0 to 9. The place value is based on powers of 10, the number base of our system. We have a base 10 number system. Any idea why we might have a base 10 number system and 10 digits? And any idea why that happens? Do you know why it's easy, though, Ariel? I mean, we think of it as that. You're right.
Well, for one thing, we have 10 fingers.
That's why. We have 10 fingers.
Oh, well.
Okay? So we're very quickly going to encounter some other number systems where they use different things for different reasons. Okay? Ours is the 10 digits, is our digits. In fact, that's actually what we call the ends of our hands if you use it in other languages sometimes even, right? They're digits. One of the facts that I want you to recall is this powers fact. So if you have a to the n, it means a times a, n times. I know we've talked about that before, but we're going to see it used frequently in here. So I just want to make sure that everybody's clear. Okay? All right, the Egyptians are first. They have some wonderful symbols. These are them. The vertical staff. The vertical staff has a value of 1, which is convenient because it already looks like the number 1, right? It's handy. The heel bone. You kind of see that as a heel bone, right? It's a heel bone. Has the value 10. A scroll has the value 100. The lotus flower. What do you think it is? 1,000. You're seeing patterns, right? The next one is a pointing finger. What is it? Well, it's worth 10,000. The next one is a pollywog, a burbo fish, or a whale. Different resources that I've used have called it different things. Your book calls it a pollywog. It's so cute. It looks like a fish, right? A little tadpole or something. It's worth 100,000. And the last one is an astonished man. And I think he's astonished because he's worth 1 million. That's just my take on that. And the way that these looks different depending on the resource you get. And I'm going to guess it's kind of like us with our, writing. My A doesn't look exactly like Ashley's A, right? It's a handwriting kind of thing. So I'm guessing that's part of it. For example, the astonished man in one of my books that I've used to teach this before looks like this. Okay? So I just don't want you to look at this and go like, well, she drew it like that, and I see it over here on the internet. It looks like this. She doesn't know what she's talking about. They come across in different ways. In particular, the astonished man and the lotus flower has a slightly different view too when you see it. And those are the two that are kind of more complicated to draw, so it kind of makes sense that those would have some different picturing. All right, in their system, it's very simple in the sense that to get a number multiple times, like if you want 5,000, you draw 5 of the 10,000 value. So let's take a look. This one right here, we're going to go from their system back into ours. We see, I'm taking a look at that. That's part C. First it says what comes before this in their system. Let's do this one at a time. We have 3 of the scrolls, and then we have a heel bone, right? The last digit, the heel bone, what's that heel bone worth? 10. It's worth 10. The heel bone's worth 10. So what number would come before 10? 9. So if we want to know what number comes before this, we write the first three symbols the same, and instead of writing the 10 at the end, we need to write a 9. And how would we write a 9 in their system? 9 of the vertical staffs. And sometimes you'll see them stack these, so you might actually see this.
Is that where tally marks came?
Tally marks are done a little bit differently, but it's the same idea. Yeah. So you could write it either stacked or like this. Usually they don't stack anything until you get to about 6. If there's 6 items you're drawing, you'll see some stacking going on in some resources. Sometimes you don't see stacking in anything written down. Egyptian numeral. What would come after 10? 11. And that's actually the easier one to do. So we've got the same number we started with, plus this one, and then I have one single digit afterwards. So I don't have to know what the whole value is to actually know the number before and after it, right? That's actually true of our system as well. We just changed the last digit, right? You change the last digit to get the numbers before and after whatever number you're working with. Now, we are going to talk about what this value is, however, in our system. So in our system, we know that the last value is worth 10. What is a scroll worth? 100. So if I have 3 scrolls, it's worth 300. So I'm going to write it out just so you can see it. Basically, this is saying 300 plus 10. Right? Because the heel bone's worth 10. This is the grand total of the number 310. You don't have to write down 300 plus 10, but that's essentially what you have. Each of the pieces sort of combined with addition, really. Okay? Now we're going to go the other direction. We're going to take one of our numerals and we're going to write it in their system. We're just going to start with the 2 at the beginning. That 2 is in our 10,000s place. What is the 10,000s symbol for them? A pointing finger. So how many pointing fingers do I need? 2. I don't draw well, so I promise I'm not going to super analyze your drawings. Just make sure I know which symbol it is you're trying to draw. Okay. Okay, the 10,000s place we took care of. Now we're in the thousands place. What's the symbol in the thousands place? The lotus flower. So how many lotus flowers do I get to draw? 3. The next one is a 1 in the hundreds place. What is the hundreds place symbol? Scroll. So I get 1 of those because there's just 1. 4 what? Heel bones. And then 5 staffs. And please do not tally mark it and cross it like the hash mark thing. That's not something they did. Okay, so it is 5 staffs vertically. That's it. No creativity allowed because we did not create the system. They did. Okay. Okay, that's really all we're going to talk about with the Egyptians. A few thoughts about this. You'll notice it's pretty simple to read and write it. There's nothing really terribly difficult about it. However, it is cumbersome. It's long to write it out, especially if you had 9 digits of something, right? 99,999. You want to do that one? I don't. So there's sort of that negative effect. The other thing that you might have noticed, or when I say it, you'll be like, oh, I didn't think about it, is there's no 0. Right? There's no 0 in their system, which could lend itself to some problems, right? Yeah. All right, the next one we're going to look at is the Babylonians. Yay for the Babylonians only having 2 symbols. It's much better. The other one had lots of them. This is 2. But you'll see that that has some drawbacks as well. The first symbol looks kind of like a triangle where the point part is downward and the base is upward. You kind of think about it as the word upside down, but that's just because we draw triangles the other way. Maybe we're upside down. And that value is 1. The other one looks like an arrow, or when we draw it, we're probably just going to draw it like this. So it kind of looks like a less than sign. And when I draw, I'll tell you, when I draw the triangle, I'm going to draw it and not shade it in, because it just becomes annoying, shading them all in. Okay? That's actually worth 10. Hopefully you're looking at that and thinking, okay, but if I had to write the number 1,000, what do I do? because I'm not writing that many tens. No, we're not. They actually have a place value system kind of like we do, right? So when we have, say, a 9 in the hundreds place, we recognize that that's not 9, it's 900, correct? They have the same sort of thing, but their place values are not base 10. They actually have a base 60 system. Okay? So in our system, for instance, here's the ones place on the far right, and our next place value be worth 10. Well, theirs is worth 60. And our next place value be worth 10 squared, which is 100. Theirs is worth 60 squared, which is 3,600. And then it'd be 60 cubed, and then 60 to the fourth. And so you can get really large numbers very quickly because you square and cube 60, which is a very large number.
What if we're trying to get to a number that's not like a baseline of 60?
I'll show you what you do when you're working with that. I think the next problem actually works pretty well for that, okay? Here is a symbol. Oh, yes.
Where, if we got like the 10 because of like 10 digits, like 10 figures, where would they get the 60?
The Mayans are an easier one to describe where they're getting theirs from. The Babylonians, I am not sure where the 60 comes from. Why they chose base 60, I really don't know. Not on that one. Yeah, sorry. Mayans are so much fun, though. Y'all are going to love them. All right, let's take a look at this. Here is a numeral in their system. You see lots of arrows and triangles and fun stuff, right? So a couple of facts that you need to be aware of. If you sort of think about it from right to left, back this direction, you can count their place values easiest. So they would always put the 10 before the 1. So this is all in one place value system. Okay, that's the ones place. Everything that I just sort of underlined is the ones place. Okay, so the ones are on the far right, and the tens are next to them. So this is the ones place. And then this would be the 60s place. Okay? I'd like for you to count what's in the ones place. How many are in the ones place right now? There's 9 ones, but how many tens are there? There's 5, so there's 59 right now in the ones place. Does everybody see where I got the number 59? Okay, so let's do the easy one. The easy one is what comes before 59? 58. What would I do? Well, just draw one less of those triangles, right? Sure. So we're going to draw the first single triangle. We're going to draw the 5 arrows. And then we're going to draw 8 triangles at the end. That's not bad, right? Just take one off. But what happens when we do the number after? What comes after 59? 60. But you can't put 60 in the 60 in a base 60 place. It's like I don't have a digit for the number 10, right? If I have 10 of something, it comes from a 1-digit number to a 2-digit number. I have to use another place value. The same thing here. Once I hit 60, I don't have anything, and I have to round up to the next place value. Are you guys with me? Right? Like it's like having the number 19. What comes after 19? Well, it's not a 1 and then 10 more ones, right? We make this a 0, and we increase this one by 1. That's what we do. That's what they would do as well. They're going to make that last place value non-existent, and they would increase the first place value by 1. And already you should notice this is a problem. Do you notice what the problem is? There's 2 triangles. That's not a problem just yet, but
How do you know if it's 1 or 60?
yeah.
Value?
There's nothing for me to put right here that's a 0. We have a 0. They didn't. How, when I look at this number, do I know that this is supposed to be 2 60s and not 2 1s? How do I know that this is the second placeholder from the low right? And the answer is I don't. I just don't. That's a problem, obviously, because if somebody owes you $0 and somebody owes you $60, or not 60, but if somebody owes you, I didn't say that right. If somebody owes you $2 or somebody owes you $120, you would want to know which one it was. For bookkeeping, this would not be good. All right? Obviously a problem. So this could be, this value could be interpreted as the number 2, Or it could be interpreted as 2 times 60. That's 120. That's what we meant it as, right? That's what we meant it as. But there's really nothing that says it couldn't also be like 2 times 60 squared. 2 times 60 cubed. There's nothing. There's nothing that prevents that in their system, which obviously makes it highly unhelpful. So that would be the problem with this answer in part B.
Okay, hold on.
Yes,
I'm
ma'am.
super confused. How did we get from the first number to this being, because the first number is 59, right?
This piece is 59, yes.
Okay, but all together it's 59.
No, the number before it is worth 60 because it's in the 60s place. The number after it's worth 59 because it's in the ones place.
Right, but I mean like that whole thing together
Right.
is 60.
No, the whole thing at the beginning is 60 plus 59.
It's two numbers.
It's two values added together. It's really what we do with our system. We just don't think about it that way. Like when I write down 38, it really means 30 plus 8, right?
Yeah.
That's what they're doing as well. This number means 60 plus the value over here, which is 59.
Okay.
So if we increased it by 1, it would be 120, right?
Yeah.
But how would we write that?
That whole thing added up to 60 and I was
The part that was in the circle did. 120, yeah. It's okay. You're good now? Okay. Yes, Amy.
So, like, just to be certain, how do you know which one's in the ones place and which one's in the 60s place? Like,
They do a couple of things. Your book actually likes to put spaces between things. I'm not sure how accurate that is because I haven't seen that in any other resource. But like if they were drawing this in your book, they would do this.
okay.
Like they would do something like that. So they were going to sort of draw in a space here. Okay? Just practically speaking, what they obviously would do though is that if you went from a larger symbol, this is worth 10, to a smaller symbol before it, that definitely indicates a place value change. So even without a space there, that would have to be a place value change. But you can also imagine that this would be awkward as well if you had, say, a 1 here and a 1 here. So if you think about over here on this picture, all the things that I just told you it could actually be 60 plus 1, which would be 61 as well. Because it could be a 1 in the 60s place and a 1 in the ones place. You with me? Especially if I didn't see that space very well, even if they really did put spaces there. I mean, how big of a space does it have to be to really be a space? That's kind of ambiguous. So we already said what the original number in their base was worth what? 119. The original number that we drew was worth 60 plus 59 was 119. If we do this number, I mean, it could be worth 120 is what we meant for it to be worth when we added 1 to it, right? That's what we meant for our new value to be worth. But the original number was worth, this value should say original. The original value was the Hindi Arabic, or the original value given. All right, you ready to see how we change our number into their number? Okay. This is the longest kind of a process, and it's a little bit awkward, but you're going to see me do it several times with several number systems, and it works the same way for all the number systems, okay? Because it's base 60, we need that information. We have the ones place. We already said we have the 60s place, and then we have 60 squared. And what is 60 squared worth?
It's like a lot.
3,600, right?
Yes.
Yeah. It's the value in that where that line is. What would 60 cubed be? Somebody find that for us?
216,000.
Okay. I'm going to stop there, and here's why. I need to only go as far as how big my number is to begin with. The number I have is 43,205. So I only need the numbers that are smaller than it. So I do not need that first number that I just wrote down. This one's too big. 216,000 is bigger than 43,000. Okay? So I'm going to need 3 placeholders for the number I'm working with because these are the numbers that are smaller than 43,000. What we're going to do is imagine I had 43,205 crayons. And I came into class and I dumped them on the ground. And you guys would be like, ooh, crayons, let's color today, right? I would be like that because that looks like fun. But we're not going to do that. We're going to organize them because I like to organize too. We're going to organize them in bags that are worth 3,600. So we're going to take some crayons and put them in bags that are 3,600 bags. We're going to, after we fill up those, and we can't fill anymore because we don't have enough left, we're going to fill up bags that are size 60. And when I don't have enough of those, we're going to fill up bags that are size 1. We're going to have all the singles left over. You know, the junk drawer ones. Are you guys with me? Okay, we're the crayon manufacturer.
Or like,
Yeah.
so we're gonna get 3,000.
I have 43,000 crayons all on the floor.
Okay, so you're gonna put 3,600 in one bag.
Yes, and then I put 3,600 in another bag, and 3,600 in another bag. My question is, how many 3,600 bags can I have? How would you do it? You would divide. This is a division algorithm. So what we're going to do, and I'm going to show you how to draw it because it's kind of a handy way to do it, is we're dividing by 3,600. What's the 100, right? 3,600. Now, I'm going to draw it interestingly, and I'll explain it as I go. 43,205. Okay. The 3,600 is on the left. The division of what I'm dividing is the 43,000. And your calculator is going to be a very helpful tool right now. So if you were to divide that, I want to know how many whole numbers it will go into it. How many whole number times does it work? 12. I'm going to put the 12 on the right-hand side instead of on top. I know we normally do our division, we put it on top. But I'll show you why in a second. There are 12 times 3,600 crayons that will go into bags this big. Next thing I need to know is what is 12 times 3,600?
7,000.
How many?
7,000.
7,000 sounds too small.
43,200.
43,200. Almost all of them. Oh my goodness. And then I'm going to subtract because that's what you do with division next. What do you get when you subtract this? 5. Am I going to be able to make any bags of size 60? I'm not. But for the sake of my division algorithm, I'm still going to write in the 60 next and write down that I have 0 bags of size 60. I'll show you why as we keep going. Just trust me, you want all of the factors of the division written on the left. And of course, when you subtract that, you get 5 again.
So would that one be the bag of
Yes.
one?
These are the bags of 1, or the single crowns that are left over. And there are 5 of them, obviously. And we always go clear down to, oops, I didn't mean to do that. We always go clear down to having 0 left. My answer in Hindu Arabic is here, 1205. These are the numbers I needed. Okay? Yes, Emily?
If you like stop when you have 0, how do you know not to stop at the first 0 and then?
Oh, because I still had 5 crayons left. This 0 is because I subtracted it off and it was 0. Here, when I did 5 minus 0, I had 5 left. So I'm not going to stop until I've got 0 as the remainder left. Yeah. Okay. 1205. How do I write a 12 in Babylonian? Arrow and 2 triangles. How do I write a 0 in Babylonian? You don't. That's exactly right. You might leave a space, but how big of a space would it have to be to indicate there's nothing there? And how many nothings are there? This is not good news. Not good news for those Babylonians. We'll at least leave a space a little bit so that we can recognize that we're about to move on to another number. But the next number is going to be the number 5. How do I write a number 5? 5 triangles. So even if I leave a space, I've got a problem because I had no way to represent the 0 in the 60s place, right? So, of course, the problem is that this number might be, if you were just given this number and you saw the space, you probably would not think this is 12 times 3,600. You'd probably think it was 12 times 60. And if the space weren't recognizable enough, you might not even think that there's a space at all, and you might think that this is just 17. Are you with me? How many triangles are there? 5. Plus the 2 at the beginning. That's the 7. This is a problem, right? Not such a good... Somebody was lacking some common sense. This doesn't work very well. Okay, Mayans. They're so much fun. The Mayans have 3 symbols.
Wait, are we just like leaving it at that? Like, there's
I
just
think
a problem
that's... Yeah, there's a problem with it, but we are leaving it at that. You're right.
Like, they
Yeah.
just have a junk.
Yeah, that is how we would write it. Unfortunately, it would also have other things it could mean, which is a problem. I agree. It's definitely a problem. I'm glad we're not Babylonians. How about you? It would be a nightmare for a bookkeeper. Okay, 3 symbols for our Mayan friends. We have a dot. The dot is worth 1. We have a line, and a line is worth 5. And we have a shape that kind of looks like a clamshell. That's what it's supposed to be called.
Yeah.
It's not really meant to look like a pie. I don't have good artistic ability. If you look in your book, you probably have a much better image of it, but it's meant to look something like a clamshell. But you're going to love what this value is for the clamshell. I get a 0. Mayans made progress because nobody's had a 0 yet, right? I mean, like, seriously, the 0 has caused us problems with both of the other numeration systems, especially the Babylonian one. I need something to hold a place. I have that now. So at least I have that with the Mayans. A few facts about their system. They do have a place value system. It is a modified base 20 system. So what do I mean by modified? Well, it's not really like 1 times and then 20 and then 20 squared and 20 cubed. They do something a little bit funky in it. I'll show you in a second. It's written vertically. Okay, so we don't write our numbers vertically. We write them horizontally, left to right to left, depending on how you're reading and writing them. But they're written horizontally. Theirs are written vertically. The smallest values on the bottom and the largest values on the top. Okay? And the dots are always written above the bars within the place value. So if you had, say, the number 6, you'd write a bar with a dot on top of it. Okay? So always dots on top of bars. All right, so let's talk about this modified business because that sort of sounds a little bit funky, and it is sort of funky. So this is the ones place. It's written at the bottom. And then this is the 20s place. So far, so good, right? So normally I wrote it horizontally before, but they're stacked on top of each other. These lines I'm drawing here are not lines worth 5. They're just placeholders, okay? The next one that they have is not 20 squared. It's 20 times 18. Give me a second, I'll explain, but let me just show you the rest of it. After that, they have 20 squared times 18. They would do 20 cubed times 18. It's all powers of 20 after that. They just have this one weird step where they throw an 18 in. So let's talk a little bit about the Mayans. Why do you think they had a base 20 system? Fingers and toes. You're exactly right, Leah. Yeah. So how many older civilizations do you know that wear closed-toed shoes? They didn't. I mean, right? Think about the pictures you see of Jesus and the disciples, right? They're wearing sandals, right? Sandals. We've got sandals. We can see our toes. Yeah? Sandals and toes. So that's the 20 business. What is 20 times 18? There's something special about that number. Okay, it's 360. Why do you think it was so important for them to have the 360? Because that's how many days they thought were in a year. We also do 360 for something else as well that we can credit to the Mayans. The degrees in a circle. Okay? 360 had some sort of significance. I don't know about it being magical or anything, but it certainly was significant to them. So they wanted it to be one of their place values. Okay? Why is it mattering to us? Well, we need to make sure that when we're doing our division and such in a minute here, that we use the right place values. So our place values are 1, 20, 360. What comes after 360? That is, what is 20 squared times 18? What was it?
7,200.
Thank you. 7,200. What do we get if we multiply that by another 20? Something big, right? 144,000, which actually has biblical significance too. Do you guys know where 144,000 is in the Bible?
Is it Revelation?
Yeah, it's in Revelation. It has to do with the number that are saved during the tribulation, something like that. I can't remember the exact deal, but 144,000 is a significant biblical value too. All right, so we're going to use this information then, and we're going to create some other numerals based on the same things that we were doing before. Okay, so here's a number. We'll convert this number in a minute. That's not our first question. Our first question is, what numeral comes before this value? Now, the first thing I want you to recognize is where the place values change. Before I told you that dots go on top of the bars. So if you see bars and dots connected, those are the same value system. So this is one place value, this is the place value above it. Okay, bars, dots, one place value. Another bars, dots, another place value. Okay, so it's always looking at the very bottom of theirs to find the lowest value. What number is in the bottom place value that I squared in purple? It's 9. Because you have the bar worth 5 and the dots. So the bar and dots together make up the numeral, it's 9. Okay, or make up the value, not the numeral, but the value, 9. So you have 9. So what would you do to get the number before that? You do 3 dots. So the number that comes before this, if they were writing these sort of like, put these numbers in order, they would write, the top value would be the same, 2 dots and 2 lines. I'm sorry, 1 line. And then the next one would simply have 3 dots and a line. They just take away a dot.
I'm confused. If we said the number was 9, how is it 9 if there's 2 lines and lines are 5 each?
Because this is 9 and this is 7.
So,
You have to be within the place value. It's just like in our system. If I talk to you about the number, I'll use a different number because I don't want you to confuse the numbers here. But I've talked to you about the number 53. How do I find the number before or after? I don't do anything with the 5, right? I only look at the 3. Ariel.
Okay. So, the number we're looking at is 79.
The number we're not looking at is 79. That's not true.
Oh my.
We're just looking at the 9. Okay?
No, I meant, okay. I didn't mean for like this. I'm confused as. So the lowest number is on the bottom.
The lowest number's on the bottom. Like if we were writing our number 53, we would write 5 on top of 3.
Okay,
That's what we would
exactly-
write
why
in
is
our
9
system.
below 7 then?
Because 9 is in the ones place and the 7 is in the 20s place.
Not the lowest place
Yeah,
value, not
yeah.
lowest number.
Right, the lowest place value.
That helped me out so much.
Right. It's like if I had the number 35. Well, why is the 5 coming after the 3? Well, because it's 5 ones and it's 3 tens.
Okay.
So the numbers themselves have nothing to do with the place location that they're in. So the location that we're looking at is the bottom location. The value right now in that location is 9. So if we want the number before, we remove a dot. Okay? What would we have to do if we want the number after? Technically, we would add a dot. But how many dots would that give us? Okay, so if we added a dot, we'd have 5 dots. We would not draw 5 dots in their system because 5 dots has another way to be expressed as a line. So instead of having 4 dots in a line becoming 5 dots in a line, we have the same 2 dots and lines as we had before, like that. And then we will now have 2 lines. Kind of looks confusing now, doesn't it, Bridget? I thought we were going to fix some of these problems when we had a place value 0. So what we mean is we mean that there's 10 here and there's 7 here. That's what we mean, right? But it's kind of hard to draw that to look like that for real, isn't it? How else could we interpret that value that we just created?
3 different place values.
Maybe, or one place value of 17. It could be the number 17, right? Because that's actually small enough to count up to 20. It's this whole number, if it were one value, could just be 17. But you're right, Abby. It could be that each of those pieces are a different place value too, couldn't it? It could be that I have 5 in the ones place and 5 in the 20s place and 5 in the 360s place and 2 in the, where am I at? 72,000s place. We don't have commas. We don't have anything to distinguish them. This is a problem. Agreed? Yeah, this is definitely a problem. So this could be 17. Or it could be, this is the one you guys were just talking about, 5 times 1 plus 5 times 20 plus a 5 in the 360s place plus a 5 in the 72,000s place. So this number legitimately could be 16,305. So it's 17 or it's 16,305.
For the 72,000 would be 2.
Oh, yes, that was supposed to be a 2. I'm sorry, thank you. I just recorded it from my paper wrong. That's actually the value it should be if I end up with 16,000. Yeah, sorry, 5, 5, 5, and 2, because there's 2 dots on the top one.
So, how would you write 60,305 vertically? Would it be 16 in the 12th place, or would it be?
You would write it with 2 dots and 3 lines. That's kind of the problem. So if I was given the number 16,305 and Amy was given the number 17 and Maggie was given the original number we started with, we would all have the exact same Mayan numeral expansion.
Isn't it 7,200, not 17,000?
Oh, yeah. I think it was
How is it
7,200.
16,000?
I didn't actually have the numbers written out like that on my paper. I had the powers written out. So, yeah. Thank you. Okay. All right. Let's actually figure out what the value in Hindu Arabic of the numeral would be. So this value, the original value is what I'm talking about. The original value. So the original value would have been 7 in the 20s place and 9 in the 1s place. That's how we originally interpreted it, right? 7 in the 20s place, 1 in the 9 in the 1s place for what total? 149. So the number that we were looking at here is that we thought we were getting 150. That's what we thought we were creating. But in creating the number 150, we realized that it looks exactly the same as the number 17 and exactly the same as the number 16,305, which is highly, highly unhelpful. Okay, we have one more example in Mayan, and then we'll stop. Okay, do you remember we just did the division algorithm just a moment ago for the Babylonians? Same division algorithm for the Mayans, but we're going to use their place values, their place system values. So we have 58,532. So when we created all these numbers over here, which one is smaller than, the biggest we can be, but smaller than the 58,000? Yeah, all of these values would work, right? So our first number we're going to divide by is the biggest thing we can divide by, and we will actually be no bigger than. So 7,200. So we're going to divide 7,200 into the 58,532. How many whole number times will it go in? 8. So again, this is like me dumping out 58,532 crayons and trying to create bags of 7,200. What is 8 times 7,200? 57,600. And if we subtract, what do we get? 932. Okay, the next place value down from 7,200, don't skip any, but what would it be? It was 360. Does 360 go into 932? Yes. How many times? 2 times. What's 2 times 360? 720, yeah. And what is 932 minus 720? 212 is correct. Hopefully you don't need a calculator for that one. What's the next place value down from 360? 20. How many times will 20 go into 212? 10. 20 times 10 is 200. Definitely don't need a calculator. Subtract and we get 12. Again, a no calculator step. If we divide by 1, we're going to get 12. And then minus my 12 and I end up with 0. These numbers are the numbers I need. But I need to write it in their system. How do I write a number 8 in their system? A line with 3 dots on top. You got it. How do I write a 2 in their system? 2 dots. So I'm going to go downwards, right? It's underneath them, 2 dots. How do I write a 10, in their system? 2 lines. which is really confusing because now those two dots that I just drew with the two lines underneath them look like they're somehow connected, right? And there's no way to distinguish that they're not. There just isn't. And then I've got the number 12, which looks a lot like what I just wrote before. 2 lines, 2 dots. Obviously not ideal. Not ideal.